Imagine the universe is running on two separate operating systems. They both work perfectly on their own, but if you try to run them at the exact same time, the entire system crashes. The first operating system is a framework known as general relativity. Formulated by Albert Einstein, this is the rulebook for the massive objects in our universe. It explains how planets, stars, and galaxies bend gravity, treating the cosmos as a perfectly smooth, continuous surface of space and time. The math here is incredibly accurate when calculating the orbit of a heavy planet. But it has a blind spot. It cannot see the tiny, microscopic building blocks that actually make up that planet. That brings us to the second operating system, quantum mechanics. This is the rulebook for the absolute smallest scales of reality. It dictates the highly erratic, unpredictable behavior of atoms, electrons, and photons. We have tested both of these theories extensively, and they pass every experiment we design. Yet, when physicists try to combine the smooth math of gravity with the jittery math of quantum mechanics, the equations destroy themselves. This mathematical failure is the boundary where our most successful theories simply cease to function. It is a fundamental gap in our understanding of how the universe is actually built. Think of reality like a high-definition photograph. From a distance, the image looks flawless. But if you zoom in close enough, you eventually hit a resolution limit where the picture breaks apart into individual blocky pixels. General relativity describes a macro world that has no pixels. It assumes the fabric of space and time is perfectly smooth, no matter how closely you look. The quantum world operates entirely differently. Down there, energy and matter are quantized. Quantized means that values can only take on specific, discrete amounts, rather than blending smoothly together. If you try to force these two views together by zooming infinitely close into the smooth curve of space, that gentle curve falls apart. It becomes a chaotic, boiling sea of particles, known as the quantum foam. This is why the math fails. You cannot have a reality that is perfectly predictable and violently jittery at the exact same time. To see this glitch in action, we have to look for a place in the universe where extreme gravity and microscopic scales are forced to exist together. We find that exact scenario inside a black hole. A black hole is formed from the collapsed core of a dead star. It contains an immense amount of gravity, meaning we absolutely have to use the rules of general relativity to describe it. However, absolutely all of that mass is crushed down into an unimaginably tiny speck at the center called a singularity. A singularity is a point of infinite density, where the laws of physics break down. When physicists calculate what happens at that singularity using both rulebooks at once, the equations spit out an error code. The answer is simply infinity. In physics, an answer of infinity usually means your equations have broken down. It is nature's way of telling us that our current models are incomplete. Resolving this conflict requires a single framework that can handle both heavy stars and tiny atoms, a concept physicists call quantum gravity. Quantum gravity is the attempt to reconcile the physics of the very small with the physics of the very large. One of the leading mathematical attempts to build this framework is string theory. Instead of treating the smallest pieces of matter as solid, jittery dots, string theory suggests that if we zoom in far enough, those dots dissolve into tiny, one-dimensional, vibrating loops of energy. Think of a cello. You can play many different musical notes on a single string just by changing how it vibrates. In string theory, these microscopic loops do the exact same thing. One frequency produces a particle, like an electron, while a different frequency produces a quark. By replacing erratic dots with predictable strings, the math begins to behave. Matter, energy, and gravity finally share a single, consistent mathematical framework. While the math of string theory is beautiful, we do not yet have the particle accelerators powerful enough to test it. We are currently caught between two accurate but incompatible truths, waiting for a way to verify how they connect. The mind that bridges the gap between massive planets and jittery atoms will provide the first complete description of how the physical world operates.